Hello all. Now let's continue to the second part of the 19th lecture. So last time we saw about non-idealities in the BJT. Now let's talk about the uh, temporal profile, in the sense that how much time does it take to uh, for the minority carriers to cross the base, and what is the maximum frequency of operation and such. So before we begin, the first important characteristic is the base transit time. So I have a BJT. I have injected carriers into the base. Now these carriers should cross the base width to be swept across the depletion width to form the current, right? So how much time does it take to actually cross the base width, the neutral region in the base? So that's the question. So how do we find that? We first find that by taking the actual charge in the base, so this is QNB, number of minority electrons in the base, which is 0 to W, width of the neutral region, QAE. This is the area of the base emitter junction, NP naught of X. NP naught is the profile of the injected carriers, right? And if we assume that the width is very small, instead of the exponential decay, you can consider it as a linear function, right? And it will turn out to be QNB. Basically, it's a triangle, right? Half AE Q NP naught into W. NP naught is the actual density here, right? And this can be, and we also know that the collector and the emitter current are written as QDN Ni square e power Q BB by T. So with this, the actual time of base transit will turn out to be QNB by IE, which will, if you substitute, will come out to be W square by 2Dn. So the time that the electron takes to transit across the base width is proportional to the base width, of course, square of the base width. So wider the base, the slower it operates, and you can see why this determines the frequency of operation, right? The time it takes for the electron to transit through the base. So for faster operations, you need to have smaller and thinner base widths. Previously, we saw this also a reason for increasing the base collector emitter current, but even for just speed of operation, it is better to have a very small base width. But this form of the time, width square by twice dn, we will see slowly that it appears in many places, and hence it's good to have a feel for this form of an expression. We have assumed constant doping density, but then if we are actually, the base is not constantly doped, as we saw previously, for other purposes, the actual base expression will turn out to be right. So with this given, now let us consider the question of what is the maximum frequency at which we can operate the BJT, right? For now, let us see the frequency of operation. So previously we shown that it takes a certain time for the electrons to transport across the base region. So this automatically gives you a feel that you have some sort of an effective capacitance in this BJT device, right? So if we take a block diagram of something like this, you have V in, I in, I out, something like that. right? So you can see that you have we can write a relationship such that I out is some gm times V in. Gm is called as the transconductance. It's typically conductance because it is current divided by voltage, and it is transconductance. I mean, it is basically transconductance because it relates the output with the input. Okay, it's not the same thing. So another way to write Gm is d I out by dV in, and we know this I out IC from the previous expressions to be QIC by KT. We have previously defined the GM in our PN diodes as well. It will turn out to be having the similar expression. So GM can be proved to be following this particular expression. So we are considering this block diagram to show that this BJT can be considered to have an effective input impedance CIN, because we are considering that it does not have an infinite operating frequency, and hence it takes a particular time to switch this device, and there is a particular maximum operating frequency. So there exists a capacitance in this particular device, and let's look at what are all the capacitances that is possible. So let's say that we are going to divide this into an NPN format. You have a collector, you have an emitter, and you have a base and you have an emitter, right? Under this situation, we know about certain capacitances, right? You know that your collector base has a capacitance. This is C depletion collector base, depletion capacitance, right? You have an emitter base depletion capacitance, right? And we saw that because of the minority carriers here, a PN junction have a diffusion capacitance. Why are there no diffusion capacitance in the reverse bias base collector junction? I'm going to put it in the small d. The reason is because you don't have many minority carriers, so you do not have a large diffusion capacitance in the reverse bias junction. However, in addition to that, you have what is called as a space charge capacitance. We will deal with it very shortly. Right. So this is the emitter, which is typically grounded, and you have a collector here and you have a base here. In addition to that, you have what is called as a parasitic capacitance, which is all lumped together and put in this particular fashion between the base and the ground, right? So basically you have a C parasitic capacitance. So this is the sum of all capacitance that are present, and you can see that they are all connected in the parallel fashion. So you have a C in is some summation of all the capacitance C parallel plus C space charge plus C depletion in the collector. You have depletion in the emitter, and you have an electron diffusion, and you have a hole diffusion in the base emitter junction, and you have finally, oh, that's it, right? That's it. So one can define a cutoff frequency, a frequency of operation, which is 1 by 2 pi, all the capacitances and the resistance in this particular junction. So the resistance is typically expressed as 1 by Gm, right? And this C, I'm writing it as C total or C in, is basically a summation of all capacitances. So we will have 1 by 2 pi summation of C individual capacitances by Gm. So this is a function. This basically this plays the role of the time taken to transfer between the base transit time, right? So basically this is what it particularly defines. So let us calculate Ci by Gm for most of these capacitances. we know that the depletion capacitances have a particularly simple form. CD, either emitter or capacitor, is basically dq, the depletion, by TV, base or the collector, and it will most often turn out to be epsilon s by width of the depletion. It's either A or C, and we know that depends upon the potential. And we will not dwell much into this because we have seen this a lot previously. And we also know about the diffusion capacitance, and we know the total diffusion capacitance turns out to be q square by 2 kt lp pn naught plus ln np naught e power qbbe by kt. So this is the total capacitance. So from this we know that CND by GM, because this is what is the term that we want to find, will be QW square IC by 2 kt dn by GM, right? Because you can replace NP naught e power QVB by KT by IC, right? So this turns out pretty straightforward. And GM, we previously found GM to be QIC by KT, and if I replace them, it will turn out to be W square by 2 dn. And I would like to remind you that this is the same as W square by 2 dn that we saw when we just calculated the base transit time, right? So this is the transit time. This is the capacitance dominated by the diffusion current. Now let us take a look at the capacitance, diffusion current of holes, which is q square by 2 kt lp pn naught e power qvb by kt, and this by gm, remember, right? And gm is qic by kt, so I'm going to substitute that as well. So I will get q square by 2 kt lp pn naught e power qvbe by kt multiplied by kt by q with by ae qdn np naught e power qvbe by kt, and this will turn out to be nb, width of the emitter, width of the base, by 2 ne dm. And you can see that even this falls very closely with our previous expression, right? If so we write this as we wb by theta dm, and theta is obviously 2ne by nb, right? So with the diffusion capacitances kind of sorted out, now let us take a look at the space charge capacitance, which is nu. In addition to the depletion capacitance in the base emitter junction that we previously saw, right? So now let us consider the space charge region in the base emitter, in the collector base junction. So we have some base depletion space charge, which is much smaller in comparison to the collector side, because collector is weakly doped. So we have some NC here, right, and some width of the collector depletion width, right? Now because of the fact that I am injecting a lot of electrons from the emitter side, so what happens is your NC becomes reduced by some value NC, small nc. Okay, so the capital NC, so the effective charge density in the depletion is not NC, but it is NC minus small nc, which is because of the electrons which are injected. Typically it is not considered because the electron injection is small, but in the BJT we have majority, you have the minority injection from the emitter side, which is considerable in comparison with the nc, right? So you have this reduction in the actual charge, and because you have this reduction in the space charge here, you can see that it will increase the depletion width by some delta W dc, right? Because the actual depletion width is changed, but then the base charge, let's say the negative charge in the base did not change. So because the space charge in the collector side has reduced, it has to increase the width, right? So let us consider, so this is okay. So this is the physical principle of the space charge capacitance. Now let us calculate this capacitance. To do this, I am going to assume that the current injected in the collector can be written as Q Vs Nc. Nc is the number of electrons injected. Vs is the velocity of the electron, and this is the total current. This is from the normal rules relation that we have previously seen, right? And with this, you can see that Nc will turn out to be Jc by 2 by QVs. And if we have a constant VBC, that is the base collector potential, then the width of the depletion width square is 2 epsilon s VBC by QNC, NC being the charge density, right? This is what we previously saw. And you can actually write Nc into WDC square is 2 epsilon s VBC by Q. But now you see that Nc is reduced by Nc by small nc, right? And if we use these two, we can come up with the relation right. So now let us calculate the actual space charge. So this space charge is in excess, or is the change in space charge from the actual depletion charge that we saw. So this will turn out to be this area minus this one, right? So this is Q, oops, not the capital one, NC into WDC minus Q NC minus NC into delta WDC. And this can be simplified to Q NC DC by 2, which can be from the previous definition of NC, right? So CSC by GM, this is the ratio that you always want. So CSC is the space charge capacitance, is AE, the emitter in area, D by dVBE QSC, right? And by DIC, right? So if we substitute this, we can easily see this relationship will come to WDC by 2Vs. So once again, we come up with an expression for the, let's say, tau SC, something similar to what we saw before, and this is Vs because we are mostly talking about drift here because it is in the depletion width. So it is WDC by 2Vs, right? So the total cutoff frequency will now turn out to be 2 pi into KT by QIC C parasitic plus C depletion in the emitter plus C depletion in the base collector junction. And remember, this comes from GM, right? So these are the capacitances which are current dependent, and we have the other guys which are not, which are current independent, which is W square by 2 dN, the diffusion capacitance in by electrons, WE W by theta dN, diffusion in holes, plus WDC by 2 Vs, space charge in the collector, plus you have some sort of an collector resistance, right? So because you have a collector area which is large, you will also have a large neutral capacitance region, neutral collector region. So you have DC. I'm sorry, so this is not from the neutral region. So this RC is the resistance of the capacitor depletion width. So you have a RC time constant delay in for the electron to transfer across the depletion width in the capacitance. So the entire thing to be inverse is what is the actual frequency of operation. And this is something that we have previously seen. Your FT, that is the cutoff frequency, almost also has a relationship with IC, and it will raise as your IC increases, because you can see that you have this component which is independent of basically this is the dependence with the GM, right? So as IC increases, your GM also increases. As your GM increases, and you see that your frequency of operation also increases, right? So till a particular point, you have almost a linear increase in FC with IC, right? After that particular point, you have a dip, and it is in these regions your non-current dependent things contribute a lot, and it is the space charge factor tau space charge is what dominates at higher frequencies, at higher currents. So at high currents, C space charge dominates the transport and limits the frequency of operation. So to limit or to reduce or to increase the frequency of operation, you have to reduce WDC, right? So you have to reduce to reduce tau SC, you reduce WDC, and WDC you will reduce by increasing the collector doping density. But then if you increase the collector doping density, you reduce the depletion width of the collector, and this will also reduce the breakdown potential, breakdown of collector depletion, right? So in typical high frequency BJT transistors, you always have the trade-off in typical high frequency BJT devices is tau SC and V breakdown. So FT breakdown trade-off is significant. So with this treatment of various cutoff frequencies and various capacitances in BJT, we will stop here, because for the lack of time we could not go into other details of switching in BJT, charge dynamics in BJT. If anybody is interested, we can always discuss later on. For now we will stop here, and the next time let's go to MOS capacitors, and we'll start dealing with metal oxide semiconductor structures. Thank you.